Welcome. I'm now going to continue with my surfing example and test for the significance of our linear correlation coefficient that we found. So the sample correlation coefficient, R, tells us about the strength and direction of the relationship between the two variables, like wave height, and number of surfers showing up to surf at a beach. But what we'd like to do next is complete a hypothesis test to determine if that linear relationship that we're seeing in the sample data is strong enough to use as a model for that relationship between those variables for the population of data. So our null hypothesis will be that rho, so our Greek rho here stands for the population correlation coefficient. So R is sample, rho is population. So if rho is 0, that means that there is no linear relationship between our two variables, but we will be testing a claim that there is. So our alternative will be that rho is not equal to 0. So these will always be the hypotheses, always a two-tailed test. And there are certain requirements that do need to be met. We are going to assume those requirements are met. All right, so we'll do the hypothesis test, and then if we decide that we have evidence of a relationship, we move on to what's called regression analysis. So I'll get to that in a bit, but let's go ahead and think about the hypothesis test first. So we have our example where the researcher collected data for 7 days, and we had drawn the scatter plot, and now I've also drawn this line that's describing that relationship. So we'll get to that line in a moment. Let's start with the hypothesis test. So the null hypothesis will be that rho, the population linear correlation coefficient, all these long names, rho, if that's 0, it would mean that there is no linear relationship between these variables. So that's no linear relationship. And then we're going to be looking for evidence that rho is something different from 0, meaning that there is a linear relationship. So we ran the linear regression t-test, and we'll do that again here. So if you have your data in the calculator, we'll go back to stat tests. I like to scroll up to get there a little quicker. Linear regression t-test. And then we had our L1, L2, frequency 1, rho not equal to 0 for the alternative hypothesis, regression equation, we can leave blank, and then calculate. So previously we scrolled to the bottom and we found our R. And now as we're doing the hypothesis test, I'm going to write down the p-value. Now this p-value is very small. I can see that my calculator actually switched into scientific notation, that E-4 at the end. So let's just do a little rounding here. The first digit is a 2. It has a 7 next to it. So if I round to the first digit, that will be a 3, and then I'll take care of the E-4. So in the notes here, I'm just going to write down 3 E-4. So I would move the decimal to the left 4 places, and that will give me 0.0003. So that's going to be less than or equal to any alpha that we could ever be given. And in particular, we're going to do alpha is 0.05. So that p-value is certainly lower than 0.05. So p-value low, let the null go. We do reject that null hypothesis. So we say that our value for R, so in statistics, we say our results are statistically significant. So statistically significant always means we've rejected the null hypothesis. So therefore, there is enough evidence to conclude a linear relationship exists between wave height and number of surfers who show up to surf at this beach. All right. So if there's a relationship, then we try to describe that relationship, and we do so by finding what's called the least squares regression line. So again, another long name. So we'll sometimes just say regression line, also the line of best fit. So the line that best describes that trend that we're seeing. So given the forms here again, y hat or y prime for the regression line, y value, I'm going to use y hat, and we're going to write it in the form a plus bx. So let me take care of that part first. All right. So the value y represents what we actually observed in our study for those 7 days. But now we're trying to find the equation of the line. So y hat will be able to use the line to make some predictions. So let's start with the line. So at the top of the calculator, you'll see y equals a plus bx. So let's write down the a and the b. And I'm just going to round to 1 decimal place to make this simple. So a here, 1 decimal place would be 0.1, and b would be 10.8. So the equation of our line, so it's also called the line of best fit, we'll use y hat, and it's a 0.1 plus b 10.8 times x. All right, so that's the equation of the line. So the idea is we can now use that line to make some predictions. And in particular, we're going to predict how many surfers will show up on average on a day when the wave height is 2 feet. So we didn't collect any data for wave height of 2 feet, but I can now make some predictions. So where x is 2, the value on that line. So any value on the line is represented by x, and then our y hat, our predicted value. All right, so let's take care of that. So there's the regression line. So when x is 2, so x equals 2, so our y hat is 0.1 plus 10.8x. So we'll substitute 0.1 plus 10.8. I'll do an asterisk for times, and then we replace x, substitute x with 2. And then we can enter it on our calculator just like that, 0.1 plus 10.8 times 2. So I predict that when the wave height is 2 feet, on average, 21.7 surfers will show up. So on any given day, this would have to be a whole number, of course. You can't have fractions of surfers showing up, but this represents on average for every time you have a wave height of 2 feet, on average, 21.7 surfers are expected to show up. All right, next, we're going to interpret the slope of the regression line. So let me just come up to my other bit of information here. So the coefficient of x is our slope. So we're writing it in this form. So the coefficient of x will be our letter b. So b here represents slope. And you may remember slope is change in y over change in x. You may have heard it also just referred to as rise over run. So on my picture here, when we have the equation of the line, so we're going to refer to any time x increases by 1 unit, the change in y will be our slope. So let me show you what that looks like for this problem. All right, so our slope is our b value, the coefficient of x, 10.8, but I'm going to write that over 1 so we can do some interpreting. All right, so change in y, slope is change in y, and our y value was number of surfers. So the change in the number of surfers over the change in x, and x was the wave height. So when we see this phrase, for an increase of 1, they're referring to interpreting the slope. So that's why I wrote the slope over 1. So when the wave height increases by 1 foot, the slope here is a positive number. So I would expect an estimated, if the slope is positive, then I would expect an increase. So if x goes up, y goes up for positive slope. And I would expect an increase of, so the change in number of surfers would be 10.8. Okay, and that is how you use the regression line called the line of best fit to make predictions, and we can also interpret the slope. So the last thing I'll add here now is just we did find the coordinates of that point. So I just wanted to put that on my picture. So when x is 2, I predicted that 21.7 surfers would show up, and you can check out the video on how to graph that line on your calculator, that regression line, if you would like. But otherwise, that wraps up our beach wave height surfer problem.